All right. So going back to review here, let's take a look at some questions that deal with free radicals. So this is still free. It's still fair game for this exam. It was covered in Chapter 10 of Organic Chemistry 1. We didn't see a lot of it in Organic Chemistry 2, but just to remind you, and then I also have some students that are interested in things like MCAT and DAT, et cetera, so they might write a standardized exam with organic chemistry in it. And so in terms of least stable radicals, there's one radical in here that should hurt your eyes when you see it, and that is this one, okay? If you have a vinylic radical, that is highly unstable, okay? So anytime in organic chemistry you have a double bond and you see a radical on one of the carbons, or a double bond and you see a positive charge, those are huge no-nos in organic chemistry, okay? You never see that. So a vinylic radical is highly, 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 highly unstable. As far as which one is the most stable, this one here is going to be the most stable. And the reason why is because it is allylic, okay? So you could actually draw a resonance form for this one, okay? But you can't, well, it's not that you can't for the others, but the vinylic is very, very unstable. So moving on from that one, the next one that I had on the list was question number 5. So let's take a look at question number 5. It just says, what is the expected product of this reaction? So this is just a bromination. So where is the bromine going to go? Well, if you remember the initiation, propagation, and termination steps, the initiation is forming the radical, but then once you form the radical, during the propagation, there's 2 steps. There's hydrogen abstraction, and then there's halogen abstraction, okay? And so when you do the hydrogen abstraction, that's going to occur where you have the most, where you would form the most stable radical. And so not only is an allylic radical stable, but also a benzylic radical. So if you have a radical at this position, this is highly stabilized. Why? Because you can draw so many resonance forms for it. So where are our benzylic positions? We have one here and we have one here. Let me use different colors. So we have one where the blue circle is, and we have one where the green circle is. So which one of these is going to be, or we're going to produce the most stable radical? Well, if I produce a radical here where I have the blue, okay, that would be secondary benzylic, but where the green is, that would be primary benzylic. So secondary benzylic would be more stable, and so that is why you would end up forming this preferentially, right? Because the intermediate would be this one here. So let me just pencil it down here quickly. So CH2, CH3. Okay, you'd end up producing this radical, which is secondary benzylic. So secondary benzylic radical. Okay, let's see here. Question number 9. The Beatles write a song about that. Number 9. Anyhow, number 9, the copolymerization of vinyl chloride and vinylidene chloride, and you see their structure shown here, by free radical catalysis produces a polymer. Hey, what do you know? Chapter 27. So this is chapter 27. The polymer that's found in food wrap, you mean saran wrap, I think. But anyhow, which structural unit would appear in the polymer? So if you remember, what we do is we take the vinyl chloride, the CH2, CHCl, we get rid of the double bond. Then we put the vinylidene chloride, CH2, there we go. And then that would be the structure of our polymer. So we look through each one of these and we try to find it. And you can see that it is B, as a matter of fact, that is the structure of our polymer. Okay, so this is, again, chapter 27 chemistry. I kind of doodled on this part here, which I'm going to need. So I'm just going to move this out of the way a little bit down here because we want to cover question 11. It says, which is the correct representation of the polymer formed by the free radical polymerization of this monomer? So this is propylene. This is propylene or propene, either way. But from that, we're going to make polypropylene, which is going to look like this. We're going to have CH2, CH3, right? This would be the repeating unit that we're going to have, something like this, okay? And so we just look for that repeating unit, and we see that the repeating unit is this one here, is going to be D. And there you have it, okay? So a little bit of free radicals and a little bit of a little bit of polymer chemistry in there. Okay, let's talk about redox for a few minutes. So this section deals with oxidation and reduction, and we looked at a lot of oxidation and reduction in organic 2, only a tiny bit in organic 1. But in the first one, it says which reagents are best for carrying out this reaction. So we want to reduce the ketone, but we selectively do not want to reduce the ester, right? So this is an ester, and this is a ketone, okay? So does anybody remember which conditions you would use to do this? Out of these 4, A, B, C, or D, does any of these look familiar to anybody? To reduce a ketone selectively, but not an ester. The answer is going to be sodium borohydride, right? That only reduces the ketone. This one here, this is a Clemenson, so Clemenson, and that would remove everything, right? If you did a Clemenson, you would end up with this, right? You would just burn off the entire carbonyl, so that's not good. And then in C, you would reduce ketone and ester, so that wouldn't be any good. And then this one here, this is used to make a hydrazone, so this is to make a hydrazone, so that's not going to be useful for us. So in this case, selectively, sodium borohydride, again, so NaBH4 is only used to reduce aldehydes and ketones only. It doesn't reduce carboxylic acids and esters like lithium aluminum hydride can. Okay, now question number 4. Here's a chestnut, one that's really near and dear to all of our hearts, which is ozonolysis of an alkene. Here it says a terpene. You don't have to know what a terpene is, but you see that it ends in -ene, right? And we only have alkenes in here. So it's just which compound, when you perform ozonolysis, step 1 is ozone, step 2 is DMS. Which one's going to give you these 3 compounds? So you could try the little exercise where we break this bond and this bond, and then you would put a carbonyl here. Then for this one, you would put a carbonyl here. So let me just try to sketch it in the orientation they have here. And then for this part here, you would make this. And you can see that this must be the right answer because these are the 3 pieces we have here. Kind of the dead giveaway that it's not B or D is if you were to break this bond or this bond, in that case from the top, you'd end up with formaldehyde, right? And there's no formaldehyde, right? Same thing here, you would end up with formaldehyde, and that is not one of the compounds, okay, in there. And then for this one, there's a gem dimethyl, and there's no geminal dimethyl in here. So the answer has to be A in that one. Number 6, let's take a look at question number 6, reduction of a triple bond. So if we want to reduce a triple bond to get a transalkene, this is one where you just kind of have to memorize the reaction, and this is sodium metal reduction. If you remember in our textbook, you usually put liquid ammonia, and this proceeds through the radical anion. Okay, I didn't ask you to memorize the mechanism or anything, but I said you should know it proceeds through the radical anion. Also, I just want to point out that when you see hydrogen and deactivated palladium, deactivated is the same thing as saying Lindlar's catalyst. And so in that case, you would make the cis. That would give you the cis alkene. So I'll just put here cis alkene. Okay. Question number 11. Where is it? Over here. Well, not there. Over here. There we go. Okay. Which product would result from this reaction? So we're doing potassium dichromate. So we're doing an oxidation with this compound. So if you remember, potassium dichromate is a very strong oxidizing agent. It would oxidize, if you have a primary alcohol, it's going to oxidize that to a carboxylic acid. Okay, but if you have a secondary alcohol like this one here, it's going to oxidize it to give a ketone. Okay, so you end up with a ketone, and of course you don't affect the methyl group, and so the answer is going to be this one here, the ketone, like that. Question number 12, I had that one circled. Yes, this one here. Question number 12, which of these reagents would accomplish this conversion? So we're taking an aldehyde and we're converting it to an alcohol. So this is a reduction. So obviously it's got nothing to do with D2O and HCl. It's got nothing to do with this. It's got nothing to do with sodium deuteroxide and this kind of stuff. right? Sodium sodium borodeuteride, I guess is what you would call this, right? This is a sodium, we can put here sodium borohydride, but all deuterium is just an isotope of hydrogen. It's just hydrogen too. And they want you to understand that if I replace BH4 with BD4, okay, that the first thing that's going to happen is you have your borodeuteride ion. So if I do this, and the first thing is that the deuterium is going to go here, right? So the deuterium ends up on this carbon like that. And then after the aqueous workup with water, right? Aqueous workup puts this proton off, okay? So if you're wondering, why do they do this? Why do they put in things like sodium BD4? It's to kind of partially test you on the mechanism, that you understand what the heck is going on in this mechanism for this reaction. Okay, let's try one more from this section. It's question 13. How would you do this transformation? So if you have a cis alkene, so we're starting out with a cis alkene, and then we want to make this cis diol, right? So both of these hydroxyls are on the same side. So if we're starting out with cis, that means we have to do a syn addition, right? If both methyls are on the same side, you see they are here, and we want both hydroxyls on the same side, okay? Well, then we have to do a syn addition. And if you remember, the way we do a syn dihydroxylation is using osmium tetroxide and NMO, or you can use potassium permanganate, but either way, this does syn addition across a double bond to make a diol. So this is a reaction that was covered in chapter 8, if you want to go back and take a look at that one. Spectroscopy. Now, you're not given any handout for spectroscopy. You're not allowed to bring in any tables for spectroscopy. And this is kind of the baseline of what we expect you to know at this point. I'm not going to review IR absorbances with you. You've done that a lot in the lab. Same thing with proton. You're not allowed to bring in a table, but you're expected to know this much. And then for carbon 13, again, no tables provided, but you're expected to know this much when you step into the exam. So let's take a look at a few problems. Let's see here. Let's start with question number 2. Okay, question number 2 is the first one I had on here. We'll start with some low-hanging fruit, and then we'll get into something maybe it's a little more complicated. Just bear with me here. Okay, so if we look at question number 2, again, low-hanging fruit. If I look at the spectrum here, are there any functional groups that anybody recognizes in here right away? You're just kind of pointing at it like, hey, wait a second. There's a functional group, or there's a stretch that I know. Is there anything in here that anybody recognizes immediately? I would say the OH stretch from the alcohol, right? So this is definitely an alcohol, and then we have the CO stretch here as well. And so if we look at the 4 compounds, only one of them has an alcohol, and so the answer has to be C for that one. Thanks, Mustafa. Perfect. Yeah, absolutely. Okay, if we go over to number 3, it says, which is the most reasonable structure for a compound with this infrared spectrum? Well, let's see. You can see that we have no alcohol. There's no carboxylic acid. So we can cross this compound off because it's an alcohol. You can see that there's a carbonyl here. So there's a CO stretch, C double bond O stretch right here. So there's a carbonyl in the compound. But one thing I notice is if you take a ruler and you put it right around 3000, right? So if you draw a line around here somewhere, you notice that there's no aldehydic stretching here at 2750 and 2850. So this is not an aldehyde. So now we have terminal alkyne, and we have an internal alkyne. We have an ester in one and a ketone in another. Well, it has to be the ester. How do we know that? I'd say a couple of things, okay? The first thing is that when you have an ester, oftentimes the carbon-oxygen stretch is the strongest stretch in the entire spectrum. But even more important is that there's no sp hybridized carbon-hydrogen stretching that you would see here. This isn't even in the spectrum. And then here, this peak right here, this absorbance, this is the alkyne stretch right here. And so that's how we know that we have the internal alkyne. So If you go back to the table of infrared stretches, where was it? Up here, okay? Here it was. Triple bond, it says 2100, you know, somewhere in that range. I think it goes up to 2250. And if you look at this stretch here, you can see if this is 2021, 22. So it's right around 2200. And so this is your carbon-carbon triple bond stretch right there. So it's the internal alkyne A that has an ester in it as well. Number 4, any low-hanging fruit in this one? Does anybody recognize any functional groups in number 4? I'll zoom in on the spectrum. Any functional groups? And again, there's no trick questions in here. Any functional groups in here that anybody recognizes? Yeah, thanks, Alyssa. Absolutely. You have the OH stretch from a carboxylic acid, so I'll just put C acid here. Right, you have the carbonyl here. This would be the carbon-oxygen stretch, okay? So you look for the one that's the carboxylic acid. The only one is this one, so it must be B. Let's try number 7. Ooh, number 7. Let's see here. So let's see. It's definitely not a carboxylic acid. I noticed that there's a carboxyl group here. We can scratch that off right away because there's no carboxyl group here. Then you see that 2 of the compounds aren't aromatic. Okay, so 2 of them aren't aromatic. And so then I would ask myself, is the compound aromatic? And you can see that if you look in the, 1475, let's say around here to 1600, right? You definitely have the carbon-carbon double bond stretching that's aromatic. You have the overtones here. And so it has to be this compound, okay? It can't be these because they're not aromatic. But then I would take a look around here. So if I draw a line here at 3000, so if I put a line here, you can see that you have the aldehydic stretching. So this is the aldehydic CH stretching. This is 2850 approximately, and this is approximately 2750. So that's aldehydic stretching. This is this here, okay? Again, it's 2 signals at 2850 and 2750, usually around there. And they're not particularly strong, but you can see that they're pretty obviously showing there. All right. Let's move. And then, of course, you can see the carbonyl is here too. So this is your carbonyl from your aldehyde. Okay. Let's try which number was that? 7? Let's try number 12. Yeah, I wanted to do number 12 with you because there's 2 things I wanted to go over with you in this question 12. So in question 12, they give you an NMR and then they say, which one of these compounds is it? Well, obviously the compound is aromatic because you can see that every compound is aromatic. And so these would be the aromatic protons right here. Okay, so that's good. Now, before we get into the aromatic protons, I want to ask you guys, I have a singlet up here around 10. Could anybody tell me where that comes from? What kind of functional group that might come from? If you have a proton all the way at 10, all the way up at 10, it's really de-shielded. What functional group might that be? So if you go back, okay, if you have a proton at 10, it means you've got an aldehyde in your compound. If it's at 12, that's a carboxylic acid. But if it's at 10, it's an aldehyde. So let's go back down here and we can say the compound is an aldehyde. So here we have one, here we have one, and here we have one. Excuse me. So far, the only thing that we can scratch off is B. Now, my next question to you guys is, if I zoom in on the aromatic region, does anybody remember what it means if I have 2 doublets that are leaning in towards each other like this? If you've forgotten, when you have 2 doublets that are leaning in towards each other like this, what it means is that you've got an aromatic ring with 2 different substituents, okay? It means you have para substitution. So now if I go down here, you can see that out of all the other 3, this one doesn't have para substitution. This one doesn't have para substitution, but this one does have para substitution. So the answer has to be C. Now, we've got the para substitution. We've got the aldehyde proton. What about these 5 protons here? Well, we have a triplet for our methyl group, which is coupled to 2 protons. And then we have a quartet for our methylene, CH2, which is coupled to 3 protons of the methyl group. So there you go. So this is our ethyl group right here. And so this must be the correct compound, number or letter C. Number 13, I think, is also a good question. It's got some crazy splitting in it. Okay, it says, which structure is consistent with this NMR spectrum? Here, this is a doublet that integrates for 6 protons. Here, if you count carefully, it's 1, 2, 3, 4, 5, 6, 7, 8, 9. Where's the 9th one? This is 8, 9. Okay, so this is a non-et, and it represents 1 proton, so 1 proton. Not very pretty. Then here we have another doublet for 2 protons, and then we have a singlet for 1 proton. So I would go through all these compounds, and you can see that it definitely can't be this compound, because if it was this compound, we have a tert-butyl group, right? That tert-butyl group, all you would see is a singlet that integrates for 9 protons, and we don't have that. Then if we go to the next one, B, the alcohol always gives you a singlet, but here you'd have a triplet, and here you would have, for these two, you would have a pentet, and we don't have that. Here you would have a sextet, we don't have that. And then here you would have a triplet. So there's no triplet, so it can't be this one. If you go to D, you would get a singlet for this, you would get a doublet for this, you would get a sextet for this one, you'd get a pentet for this one, and then you would get a triplet for this one. And again, there's no triplets anywhere, so it's got to be C. And if you draw the bond line structure of C, and maybe I'll use a different color, okay? You can see why you get that non-et, okay? This proton gives you the singlet. So if you call this A, B, C, and D like this, these would be, pardon me, the hydroxyl proton. This would be your A proton, right? And B would be these ones, or sorry, B would be this one here, right? Because it's split by a total of 1, 2, 3, 4, 5, 6, 7, 8. N plus 1, you get 8 neighbors, plus 1, you get a non-et. Okay? Then you have the doublet that integrates for 6, so that would be these ones, would be the A protons, and then the D protons would be the methylene, which gives you the doublet. Okay? Okay, so that would be what? Isobutyl alcohol would be the name of that compound. Let's take a look at number 17. Number 17, oh boy, you've got a proton and a carbon-13 NMR spectrum, and just says which structure agrees with these. So if you take a look at the carbon, you can see you have 5 signals. So there's 5 signals here. And just to go over this with you, you're not going to see this on your final exam, the little S, T, and Q above the peaks in your carbon-13. But for my students that are MCAT and DAT minded, you might see these sometimes. And all this is, it's a type of coupled spectrum that can be run for a carbon-13 in place of a depth experiment. So what it means is if you see a quartet or a Q, it means you've got a methyl group. If you have a triplet, it means you've got a methylene. If you have a doublet, it means you've got a methyne. And if you have a singlet, it means you've got a carbon with no hydrogens attached. Now, we have a singlet up here around 200, so that tells us we have a carbonyl in our compound. Only way we could get a chemical shift that high is from a carbonyl. What else? So if we have a T, that means we've got a methylene, a methyl, a methylene, and a methyl. What's kind of annoying is if you look at the 4 answers, the only one that we can cross off is D because there's no carbonyl in it. Now, if we look at A, B, and C all have carbonyls in them. And then if you go to the NMR, you see you have a triplet that integrates for 3. Here you have 1, 2, 3, 4, 5, 6. So you have a sextet that integrates for 2. You have a singlet that integrates for 3, and then you have a triplet that integrates for 2. Well, if you look at all the answers, I went over these today, every single one of these satisfies 2 triplets, a sextet, and a singlet. Look, here we have a singlet, here we have a triplet, here we have a triplet, and here we have a sextet. Here we have a singlet, Here we have a triplet, sextet, and here we have a triplet. Same thing here, triplet, sextet, triplet, singlet, okay? So how are we going to solve this problem? If all of these have the exact same multiplicities, we have to use chemical shift. So I'm going to put here, must use chemical shift. Okay, so we're going to have to use some baselines here to solve this one. And the way that I would do it is I would start with the singlet, because the singlet, if I highlight that in yellow, that would be this one, or this one. Okay, now the singlet is at about 2.1 maybe. This is like 2.0, 2.1. So it's around 2.1 ppm. And it can't be this one because the baseline for a methyl is 0.9 parts per million. But if it's next to the oxygen of an ester, you would add 3. So that would give you 3.9 parts per million. So it can't be A. If you look at B and C both, right, you start with 0.9 and then you add 1 because they're both next to a carbonyl, which gives you 1.9 ppm, which is pretty close. So that's reasonable. So now it's a battle between B and C. So now we have to go to the triplet that integrates for 2 protons. So if I use the green highlighter, this one is going to have to either be this methylene or this methylene. Well, if I look at the one on the top, okay, this one here, I start with the baseline, which is 1.2, and then I add 1. That gives me 2.2. So that's pretty close, right? So this looks reasonable. If I look at this one here, I start with 1.2, but then I have to add 3 because it's next to the oxygen of an ester, which gives me 4.2 parts per million, which is way too far off. So that tells me that the answer has to be B. So we had to do a lot of work. Now, you could have solved this one without even looking at the carbon, but that's what they listed first, so I kind of went through the whole thing. You could have just solved it using just the proton, but there you go. So NMR was covered in Chapter 15. If you need to review Table 15.1 and 2, okay? That will help you with your chemical shifts and making estimations and that kind of stuff. Okay, 2 more in this section. So question number 19, I already did the math on this, so I don't want to spend a whole lot of time on this, but it just says, which compound would show a major fragment ions at 73 and 59? And if you look at these compounds, all of these compounds have the same molecular formula, all C5H12O, every single one of them. So if we tally that up, we get 88. So that means that our parent, just put here, our parent would be 88. So if we're looking for 73 and for 73 and 59, if we take 88 and we subtract 73, we get 15. So 88 minus 73 equals 15. And then if we take 88, subtract 59, so we take 88, subtract 59, we end up with 29. So 15 is a methyl and 29 is an ethyl. So we have to look for something where we could lose a methyl and an ethyl, okay? Or where we would be, prone to lose a methyl and an ethyl. Well, if I look at A, right, if I lost an ethyl group, then I'd end up with a resonance stabilized ion, okay, so that's a possibility. There's no good reason, though, for me to lose a methyl here, okay? I could lose a methyl, but it doesn't look like it would be a major fragment, okay? Here, I could lose a methyl because that would give me a resonance stabilized ion, but then I also have a propyl group over here, so there's no loss of ethyl. There's no good reason for me to lose an ethyl off of here. If I look at C, I have a methyl, and then I have an isopropyl here. So again, I don't really have a good reason to lose an ethyl. But if I look at D, all I have are 2 methyl groups and an ethyl group that I could lose to end up with a resonance stabilized ion. And so the best answer would be D. It's the only one that has just ethyls and methyl groups to be lost. All right. So with that in mind, let's try one more. And this one just says, which compound would show a major fragment in its mass spectrum at a mass overcharge of 85 and 57? So if you look at all of these compounds, I think that all are the same formula, C7H14O, like that. So that gives you a mass, that gives you a parent, which would be equal to 114. Okay, so if I take 114, sorry, 114 and I subtract 85, in that case, I'm going to end up with 29. And if I take 114 and I subtract 57, I end up with 57. And so that suggests that we have symmetry, in the compound, maybe. Okay, and that's just a maybe. But without me taking the time to go through every last dirty detail of all of these, okay, I mean, where's the place that these are going to fragment? I mean, the most common place would be around the carbonyl, because then you end up with something that's resonance stabilized here, 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 or here, something like that. But if you go through all the fragments, you'll see that the only one where you end up with two fragments that have a mass of 57 is A. Okay, believe it or not, this fragment here, the butyl fragment, has a mass of 57. And then this fragment here, this also has a mass of 57, and none of the other ones line up. And if you're wondering, what about the 29? Okay, what about the mass of 29? Well, you could lose this ethyl group here, and then you'd have something that's resonance stabilized. You don't have that in anything else. Here you have a propyl. Here you have a propyl. Here you have a methyl. Here you have a pentyl. Here you have an isopropyl. Here you have another propyl. Only place you see an ethyl that could be lost is right here. That is it. And so the answer would have to be A for that one. Okay.